Hi, everybody. Welcome to Byte Ventures, where we deep dive into marvels of technology. So, in today's video, we'll discuss about the Zomato search case study part 2, where we discuss about how Zomato handles 100 million searches every single day. So, for those who are coming new and haven't watched part 1, I would highly recommend them to watch the part 1. It'll give you a lot of context on what exactly was the problem, how we discussed one part of the solution, and yes, I'll link the video in the description for you guys. All right. So those who have watched the part one and have forgotten a little bit things. So here is a sweet little recap of the part one. So we saw that while Zomato was scaling its search engine, it faced a lot of out-of-memory exception. That was the primary use case. It was due to the field cache, and some of it were solved using a mock document that was getting indexed, but that was not a perfect solution. Eventually, they landed up into doc values, which helped them resolve the issues completely. The second part of the problem was the introduction of dynamic fields or the suboptimal design of dynamic fields. So as we discussed, dynamic fields is used in case of search because we know that there are a lot of things that can get introduced at the runtime, and we don't want to add it at the compile time to our design. For example, see this field, attributes underscore star. So what exactly is this doing? So when we add it to the indexing engine, that okay, we want to index all of the fields with attribute underscore star. That means attribute 1, attribute 2, attribute 3, and so on, right? Will get indexed automatically. We don't have to manually write that, okay, we need to index attribute 1, attribute 2, and all stuff. So this would help us save a lot of developer time because that's how this was proposed by the Solar team. But the main problem with this was there was no way to know at the compile time that, okay, this might explode, and that would lead to a problem, which is very commonly known as mapping explosion. Okay, so in this video, we'll see the part 2 where we solve for the dynamic fields problem and how could we reduce the out-of-memory exception that it got introduced by it. Okay, so let's take a step back and see what a restaurant entity might look like. Okay, a restaurant entity might look something like this. It will have a lot of other fields with it, but I'm just taking some of them just to give a little bit context of what it might be. Okay, so it'll have an ID, which is a UUID here. It'll have a name. For example, the name I've chosen is Dynamic Biryani because it's something very popular. It's probably one of the most liked dishes based out of India. Then we have entity, which is a restaurant, which is like defining a custom type of this. And then obviously it'll have a location of the restaurant based on lat and long. It can be a different thing, but for example, let's say it's lat and long for this case. Okay, so we discussed one thing, right? So when we are talking about restaurant, people do take from the restaurant from various different places. For example, this dynamic biryani restaurant can be serving in probably 50 to 100 places easily, right? But the popularity of this biryani might be better in one area or very lower in other areas. It can happen, right? Because, yeah, there are other alternatives, or they delay it, or they charge high delivery charges, or whatever it is. It can happen. So, while someone is searching for the restaurant, it is very important for them to include that, okay, how popular is it? Because people will filter it, people will group by it, and stuff like that. So, there is high chance that we should add it to the indexer so that it helps us during the search. That's what Zomato did as well. So apart from ID, name, entity, and location, we added a couple of other things, which is popularity underscore area one, which defines the popularity for the first area that we have. Popularity underscore area two, which is defining the popularity for area two, and so on. So what this 93.93 is doing is basically representing that this restaurant, the dynamic biryani restaurant that we have, is 93% popular in area 1. 25% of the people in area 2 like this restaurant or this cuisine, cuisine made by this restaurant and stuff. And similarly, we have this. But this is one of the field, right? If we go back to the dynamic fields, think about how Zomato could have introduced this. They have introduced the indexing for popularity using dynamic fields because it can happen that I want to onboard a new area which this restaurant can deliver. That will lead to addition of the new field. If we have it at the compile time, there'll be a lot of code changes that will be involved to make the search work in that area, right? So we'll probably add a popularity underscore into the indexer, and the indexer will take care of adding all of these new fields while searching or returning the documents we require. But think about a basic problem. This is just one field. It can happen to dishes, and there are other fields. Having a dynamic field in this case is a pretty bad, or I would say a suboptimal design, because that would definitely lead to mapping explosion for sure, right? Yes. So what exactly we can do in this case? So the obvious thing that comes into mind is, let's group it, probably. Okay, so can we group this to something of a popularity kind of map wherein we define all the areas inside and rather just index this, which eventually index everything inside it, probably like area 1 here, area 2 here, and stuff like that. It has this value 0.93, it has this value is 0.25 and stuff. Yes, but unfortunately, there is no such thing that was present. In other words, it would look something like the ID, name, entity, location would be the same. This popularity would be a map which would constitute area 1, have different values, area 2 having different values and stuff like that. But Apache Solr didn't have any mechanism to kind of index this. Well, we could write our own serializers and deserializers to store this map and eventually use for indexing, right? Yes, but we would not be able to leverage the indexing powers had it been provided by Apache Solr out of the box. So this might look promising at the beginning, but it didn't actually solve a lot of purpose in this case. So this idea was eventually dropped. So what's next? So Zomato thought, okay, let's do something very creative because after a lot of searches, they saw that Apache Solr supported something called as nested objects or hierarchical indexing, wherein each of the popularity is an independent object which is present inside this popularity array that we have. So this ID, entity, name, and location remain constant as like before. And instead of this having defined here, it's a array of objects that we have, right? So this is defining the popularity in area 1, which has a value of 93. This is defining the popularity in area 2, which has a popularity of 25. Okay, that seemed interesting because now that Apache Solr supports nested objects or hierarchical indexing out of the box, this would definitely make our searches pretty efficient than writing our own serializers and deserializers in the last case. Okay, let's think about this. But there is one problem. So when the engineers looked at the source code of Apache Lucene, what is Apache Lucene? So Apache Lucene is the library on which Apache Solr is built upon, right? But Apache Lucene didn't support any of this hierarchical indexing that Solr promises it has. So what exactly that means? That means Solr must be doing something or something abstraction to make this feature work, right? That's exactly right. So Solr introduces 3 different fields called root, nest path, and nest parent to solve this problem or support this feature, I would say. What exactly is a root? So root is a field that defines the top level parent document in a hierarchy. Nest path. Okay, this is a lot of text, but I'll give an example. Just bear with me for a couple of minutes. The root is defining the top level parent document. Nest path is a field that is representing the path from the root to the child itself. It's representing the whole path and separated by a delimiter like backslash or stuff. There is nest parent, so it is used to define what exactly will be the parent document for this thing. Okay, we'll see an example. So that means when these fields are introduced, we have to have these three fields anyhow. That means if you're defining our own schema, let's say the schema has only one field ID for now, but what we have to do is we have to additionally define three more fields: root, nest path, and nest parent with the type, index, stored, required fields as required, right? And there'll be a bunch of other fields, but I'm just taking that there is only one field for now, and there's three other additional fields that are required by Solr to support this indexing feature or the hierarchical indexing feature. Okay, talking about the hierarchy, we have restaurant at the root level here. So restaurant can include multiple restaurants, restaurant 1, restaurant 2. Suppose let's say restaurant 1 is here, restaurant 2 is here, and restaurant 1 has three popularity: 1, 2, and 3. That means this restaurant, the popularity of this in the area 1 is 93%, popularity in area 2 is 25%, and popularity in area 3 is 71%. The same goes for restaurant 2. That means if you are coming from a data structure background, you know this looks like a tree, so which we can call it as a root, and these are the child nodes that we have, right? Exactly a hierarchical structure. In other words, this can be a parent, and these two will be the child of this node here. That's why they're defined as C. This will be the parent for this three child that we have, or these three children that we have, right? Okay, sounds interesting, but how do I define the documents? Okay, let's get to it. So as we have defined, it'll be a nested object. So Solr gives a concept of independent documents. That means when we are defining the hierarchy, we have to define it by independent documents. That means restaurants will be present in a different document. So if we think back, we had restaurant and popularity in a single document. Now that if we have to use this feature, we have to break down the document into multiple smaller documents, I would say. So let's say this is the restaurant document that we have, and this is the popularity document, or I'd say pop document that we have. It will have the ID. Let's say restaurant 1 is ID, the entity that it is defined that it's of a type of restaurant, the name and the restaurant name, and the location. And obviously, to support the hierarchical indexing, it has three fields: root, nest path, and nest parent. As is itself is the root. So if you think back, in this case, this is the root. So that's why we have this restaurant 1 same here as well. Okay, this is the root. The nest path, that means the path from the root to itself is rest1. There is nothing else, but there is no parent. That's why this field is null. Coming to pop, that means we define that, okay, here is restaurant, here is the popularity. Let's say this is popularity 1 or popularity underscore area underscore 1. Okay, that means this is a child of this restaurant. So that means obviously we don't care about these values because this will be the same as the old things. The root, the nest path, and the nest parent will be pretty interesting to understand how this is implemented. Who is the root? So the root defines the global parent of this hierarchical document, and that will be res ID, which is res1, because the ID of the res is res1. That is mapping. Now the nest path. So the nest path is the path from the root to itself. It's res1 slash popularity underscore area underscore 1. Why is this slash? Because this is getting separated by a delimiter. We can define our own delimiter, probably a comma or a hyphen, anything. But here, take an example that we are defining the delimiter as the backslash. And the nest parent. What is the parent of this? You see that this res1 and this res1 looks similar, but it actually serves very different purpose. Okay, let's take another level which will give this clear idea of what exactly this would look like. Let's say this is C2, is another child of popularity. Let's say that's an imaginary field. So what exactly will the value of root here? The value of the root for C2 will be res1 because it's coming from the global parent of restaurant 1. The next path will be res underscore 1 slash popularity underscore area underscore 1 slash C2 or C2's ID, whatever it is. What will be the parent? The parent in this case will be popularity underscore area underscore 1, not res1. I hope that would make things pretty much clearer, right? Okay, so now that we have discussed about how creating a two different documents from a single document serves the purpose, let's dive into a little bit inferences from this. So the first thing that comes to the mind is now that there are two different documents, it will be very difficult for us to enforce field restrictions. And that's very important because, for example, the name and locations, they have meanings in context of a restaurant, but do a location or a name make sense in case of popularity? Not always, right? So that's why we can't enforce any field restrictions in different documents. Due to creation of hierarchical indexing, the size of the indexes will increase as well. So that's why there'll be a slight increase in the documents here. Then, obviously, the main goal we have achieved because now that there'll be no mapping explosion and the indexing speed or the search efficiency will definitely improve with this kind of structure. But, the interesting question that comes in is like, okay, I do have the two documents, but how do we search it? Is there a way? Yes, there is definitely a way because if Solar provides these two documents, then they have to provide something to make a search as well, which is called as block join query parser. Let's dive deep in. So block join query paradigm is kind of a option given by Solar to kind of search through this hierarchical indexing. For example, there are a bunch of documents that we have, like parent documents and child documents. Based on some child properties, you want to search for a parent document, or based on a parent's document, you need to search for some child documents. So they are categorized into two different parts. The first part that we have here is something called as child query. What is child query? So they're saying a query that matches some parent document and returns the children of those documents, right? So in this case, we would say, take a simple example. We would say, give me all the popularity uh, of the restaurant that has a name, let's say dynamic biryani that we discussed, right? It'll give that. So in other words, it can say that we can say or write this query that okay, this child of entity restaurant and return all the children's which have popularity greater than 90%. So in this case, the query will be something like not child of, not child is like a way of programming, but this emphasizes that this is a child query. This is a child of entity restaurant where the entity popularity has a value of more than 90%. That's what it means, right? Okay. The second type of thing that it provides is a parent query, where based on the child documents, it returns their parents. In other words, I would say, give me the name of all of the restaurants where the popularity in this area is greater than 90%. That's exactly what it is doing. So in this query, this will define that, okay, this is a parent query that we have, which is of type entity restaurant that we have, right? And we'd say for this entity popularity and the value greater than 90%. So this defines that this is taking value from 90% to higher, everything else. So it will be listing all the restaurants in that area where the popularity is more than 90%, right? Yeah. So this will help us give a generic overview of how things would be when we have nested documents and how do we implement indexing, how do we search or write our query to make our searches very efficient in Apache Solar. All right, I guess that's all I have for this video. I hope you liked it. If you have any questions, please post it in the comment section. I would love to answer those. If I don't know the answer, probably I'll look for it and I'll get back to you shortly. So yeah, that's all for this, and I would love to have some feedback in the comment section as well. So that's all. Thank you, and see you in the next one.